We'll start with coherence. Does anybody know what coherence is straight away? When we talk about coherence, we've got to talk about two wave sources. Yes, they must have the same frequency. Yes. Two wave sources are in phase. We'll talk about phase in a second. With each other if they emit waves which are in phase at the time of emission. Okay. The waves must have the same frequency. And I'll show you diagrammatically why that is. This will become very clear in a second if it's not now. Here's a wave. If I put a second wave in here, now I'm going to draw them like each other, just like that. These two waves are in phase. Notice that I can't talk about a wave being in phase with nothing at all. You can't have just one wave in phase with something. It has to be two waves. And you can see that they must have the same frequency, because if I had another wave that was that looks something like this, there's no way that this wave and these two waves here, this has a different frequency to these two waves, can be in phase. And what I mean by in phase, when one is displaying a crest, the other is displaying a crest. When one is displaying a trough, the other is displaying a trough. Okay? And so on and so forth. Crest, crest, trough, trough. Crest, crest, trough, trough. What would we see if we superimposed those two waves over the top of each other? Yeah, we'd see a single wave, but imagine there are two waves, two water waves, for instance. What are they going to do if I put a wave of a certain wavelength and frequency on top of another wave of certain wavelength and frequency? Yeah, we're going to see constructive interference and an amplitude increase. Yes. These waves are in phase with each other, is what we say. Which would result in constructive interference and an amplitude increase. You will all remember these terms: interference, constructive interference, amplitude, from last year, I hope. I'm going to draw two waves again. Similar situation. And this time, I know they're not identical, but they're supposed to be. These waves, what would you say? Are out of phase, aren't they? Yeah. When we see a crest here, we see a trough here. Trough here, crest here. Okay. What are we gonna see as a result? Destructive interference. This would result interference. I think everybody understands that. Here's a different situation which we are going to look at in depth. Start with a wave. Put another wave. Superimpose the wave over the top, but shift it. Just slightly. Those waves are out of phase as well. These waves have the same frequency. But are out of phase. I don't think so. No, it's not. No. Same frequency, but are out of phase. And they're out of phase by, it looks like a little bit less than a quarter of a wavelength. That's, we got half a wavelength there, a little bit less than a quarter of a wavelength out of phase by. They have, what we can say they do have is a constant phase relationship. Okay. Yes. Constant phase relationship means we choose any point in time. So imagine that this is we could draw a graph here. Oops. We could draw, okay, I'll just draw a timeline along here. So this might be time t. At any point in time t, I can choose to see what's going on with those two waves, and I will see that they still have a phase relationship which is different by 1/4 of a wavelength or thereabouts. Okay, it will always be the same. Coherent wave sources Coherent wave sources have a constant phase relationship. Here we have some yellow coloured waves. We're going to be talking mostly in this course about light waves. What could you say about those waves? Yeah, they are in phase, aren't they? These waves are in phase. What else? Yes, they do. A constant phase relationship of uh, 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 basically that no wavelength out. Well, I haven't drawn them very well, but you could say that they are a constant phase relationship of 0 between them. What else could you say? They have the same frequency. They all have the same frequency. These represent monochromatic light. If they have the same frequency, they have the same color, don't they? What we would determine as color. We know for light, C is equal to the frequency multiplied by the wavelength. And C is fixed for light, well, in a vacuum anyway, depending on the medium through which it's traveling, at 300,000 kilometers per second. We're going to assume that C is fixed. The frequency changes, and we can see here from this equation that the frequency and the wavelength are inversely proportional. If I increase the frequency, then I reduce the wavelength because this value here is fixed. Okay? We've traditionally talked about wavelength as being, or we might say that a red laser beam has a wavelength of 589 nanometers. It's in the visible region of the spectrum. And being that it's color, and only one color, we call it mono, meaning one, and chromatic for color. Okay, one color of light. Here's a relic from the past. Okay. What is this? Yeah, incandescent, we call them. Light source. And this incandescent light source, how does it work? It's basically got, we plug it into our house at home, into the socket at home, and one side is positive, the other side is negative, and we pass a current through this filament here, 240 volts at 10 amps. And this has a power rating because there's a certain amount of resistance associated with this filament. The filament, if you look very closely, is actually a spring. It's spring-shaped, and it's made of what? Tungsten. Why is it made of tungsten? And what did you say, Paul? Well, everything. If I pass enough current through you, you will emit light also. I wouldn't want to do that though. It has a high melting point. Is that what you said, Larry? It does resist current also. Yeah. Each metal has a different resistance. We put it in the spring shape so that it resists even more also. Tungsten filament. Sorry to use that analogy, Paul. I was trying to make a joke on you. uh, it's a tungsten filament. I believe tungsten has a melting point of about 4,000 degrees. Don't quote me. I'm guessing. One of the highest melting point, if not the highest melting point metal there is. So it carries electricity, and it also has a very high melting point. There's something else that we do, because if I smash the glass around here and I plugged it into a socket and switched it on, what would it do? It would blow up pretty quickly, wouldn't it? It would just basically the spring would break and we'd have no current traveling through because there's not a completed circuit anymore. Why is that? Yeah, because of the oxygen in the air. What we have in here is we still have, please. Yeah, we put it's usually argon we put in there. It's an inert gas, so it doesn't react. What we do by heating this up, by passing a current through it, heating it up, we cause it to oxidize much quicker than it normally would. If there's oxygen in the air, it's going to oxidize awfully quickly and then break. And I'm not sure what the oxide is. I guess it's tungsten oxide. I'm just guessing. I'm not a chemist, but what I'm interested in particularly here is what's going on at the physics level in that filament when I pass a current through it. Yes, the electrons get excited and then they vibrate, don't they? When the electrons vibrate, please, when the electrons vibrate, they tend to emit light. If I put a really low current through there, they'll emit light, but we won't be able to see it for a while. How will we sense that light? Yeah, you'd see it as heat first. So you could put a current through that, and you would see that the tungsten was not glowing at all in any way, but yet it was emitting heat, which is light also. If we pass a current through there at high enough rate and cause those atoms to vibrate fast enough, they will start to emit light in the visible region of the spectrum. First in the reds, the oranges, yellows, and then with enough current, they'll emit white light. What is white light made up of? Combination of all of the colors of the rainbow in the visible region of the spectrum anyway. And that's why we see this white light. If it's all colors of the rainbow, is an incandescent light source a monochromatic light source? No, it is not. This is not a monochromatic light source. Okay, next part is a new concept. You're going to have to pay attention with this one. I know that you've been thinking this is really easy. I can do all this. Oops. I'll get a new page, I think. I'm going to ask you to understand this picture. Here we have Here we have two light sources. Source 1, S1, and source 2, S2. Now I've drawn these, I've stolen this picture out of our textbook, but these sources here, if they are light, then in fact we can't see the waves, can we? And what you're probably imagining here is dropping two rocks into the pond and you're seeing the waves move out. That's one way to picture it. If I had light sources, then it wouldn't be two-dimensional. It'd actually be three-dimensional, spherical. We're just going to have a look at it in 2 dimensions, however. The other thing is, if we were in a vacuum, then we wouldn't be able to see these waves. We wouldn't be able to see the crests and the troughs, because light needs something to bounce off of in order to be able to see it. If you have ever been to a laser light show or seen a laser light show on TV, you'll notice that the lasers seem to move through the air. How is it that we see those if you can't see light unless it's bouncing off of something? Yeah, what they do is they put smoke in the air, and the laser light bounces off the smoke. If you shine a torch in a vacuum in front of you, unless it hits something, you're not going to see that it's on at all. Okay? So, if you looked into the torch, though, what's it hitting? Yeah. So, yeah. So, essentially, that's right. Exactly. It's the only reason that we know it exists, other than the fact that it carries energy, is that it reflects off things. That's right. So, here we have. Imagine these are the dark lines are crests here, and the dashed lines are troughs. Okay? Same over here for S1, crests and troughs. Have a look through here from A to B. It's actually A sub 0 to B sub 0. If I mark these points here, what are we going to be seeing at those points? Constructive interference, isn't it? Because what we're seeing is the points at which two crests meet each other. Okay, so I'll constructive interference. I'm going to mark some red dots here through P1 O1, where there's destructive interference occurring. We've got crests meeting troughs at these points. I'm not going to mark every point. Is that heater sometimes turns itself off? Is that destructive interference? I'm going to ask you now to picture this. Think about something called path difference. I'm going to choose a point in the diagram, and I'm going to be interested. This is the point here, right in the center here. What's the path difference from S1 compared to S2 at that point there? And when I mean path difference, I mean the distance from the source to the... the same was what I was looking for. I see what you mean. The path difference between the source... I have to draw it in 2 lots there. And that point there is exactly the same, isn't it? And if you have a look, 1, 2, 3 wavelengths and we're there. And it's the same over here. 1, 2, 3 wavelengths. Okay? 3 wavelengths. Path difference of 0 between them. Path difference of 0. What about this point here? Which points did I choose? What about this point here? Actually, I'll draw an arrow to it. Have a look. Watch what I do here. 1 crest, 2 crests, 3 crests from source 1. 1 crest, 2 crests, 3 crests, 4 crests. 4 crests. What's the path difference? 1 wavelength. Very good. Of 1 wavelength. Choose another point. There's the identical point. What about this point here? That point right in there. Path difference. 1, 2, 3. 1, 2, 3, 4, 5. Has anyone got it? 2 wavelengths, yeah. And I'm going to say it like this, though. Path difference of 2 lambda. 2 wavelengths. How is that for people? Not too bad? Not very good, yeah. This is a difficult diagram to understand, and we'll talk about path differences quite a bit, but in different contexts, not always in this picture. I just thought this was an easy picture to understand. Diffraction. I'm going to use the textbook definition here. Is the change in direction of travel of a wave as it passes by an obstacle whilst remaining in the same medium. Why that last part of the sentence, whilst remaining in the same medium? Yeah, otherwise we see refraction occurring, a different... oh, here, yeah. otherwise we see refraction happening. I told you I've got to pick up the pace a little bit. Here's an image of what is going on with diffraction. There's an obstacle there, there's a gap. Straight plane wave fronts on the left-hand side, moving to the right. As they pass through that gap, should the gap be approximately the same size as the wavelength of the wave, we get maximum bending occur, bending around the obstacle. Diffraction is most noticeable when the opening the size of the opening is comparable to the wavelength of the wave. Here I've got a picture. Here we've got water waves. There's an island here and the coastline, and as reasonably straight waves come through here and they approach this obstacle, when they do, they bend as they go through the obstacle. You'll notice that there's some bending occurring here, and we have waves interfering with each other. You'll also know that the shape of the coastline there. You might notice, not so much in South Australia, but in New South Wales, Sydney beaches are often like a bay, and the bay is caused by this curving of the wave fronts as they pass obstacles. The obstacles can be visual from the surface, or they can be also under the surface. Yes. Bends the wave in. Oh, like it's turning again. Yeah, absolutely. Past this obstacle, yes. So there's turning also here, past this obstacle. This is how we get the bays.